NENOMATICA, where mathematics meets YouTube excellence. Welcome to our video on comparing exponential expressions. Today, we'll learn how to compare expressions with different bases and exponents by converting them to the same base. Let's start with our first example. We need to compare the following two numbers, 25 raised to the power of 53 and 125 raised to the power of 35. At first glance, it's difficult to tell which one is larger. To compare these numbers, we'll convert them to the same base. This will allow us to directly compare their exponents. Let's use base 5 for both expressions. First, let's rewrite 25. We know that 25 equals 5 squared. So, 25 to the power of 53 becomes 5 squared to the power of 53. Now, we can apply the power of a power rule. When we have a power raised to another power, we multiply the exponents. So, 5 squared to the power of 53 equals 5 to the power of 2 times 53, which is 5 to the power of 106. Next, let's convert 125 to base 5. 125 equals 5 cubed. So, 125 to the power of 35 becomes 5 cubed to the power of 35. Applying the power of a power rule again, we get 5 to the power of 3 times 35, which equals 5 to the power of 105. Now, that both numbers are expressed with the same base, 5, we can directly compare their exponents. The first number is 5 to the power of 106, and the second number is 5 to the power of 105. Since the base 5 is greater than 1, the larger the exponent, the larger the number. Therefore, 5 to the power of 106 is greater than 5 to the power of 105, which means that 25 to the power of 53 is greater than 125 to the power of 35. Let's look at another example. This time, we'll compare 53 is greater than 125 to the power of 35. Let's look at another example. This time, we'll compare three numbers, 0.125 cubed, 0.25 to the fourth power, and 0.5 cubed. Let's again convert all expressions to the same base. We'll use 0.5 as our base. First, we'll rewrite 0.125. 0.125 equals 0.5 cubed. So, 0.125 cubed equals 0.5 cubed to the power of 3. Using the power of a power rule, this becomes 0.5 to the power of 3 times 3, which is 0.5 to the power of 9. Next, 0.25 equals 0.5 squared. So, 0.25 to the fourth power equals 0.5 squared to the power of 4. Using the power of a power rule, this becomes 0.5 to the power of 2 times 4, which is 0.5 to the power of 0.5 to the power of 2 times 4, which is 0.5 to the power of 8. Finally, 0.5 cubed is already in the form we want, which is 0.5 to the power of 3. Today, we'll solve a problem about finding the number of digits in a very large number. Specifically, we need to find the number of digits in 8 to the power of 17 multiplied by 5 to the power of 45. To find the number of digits in a number, we'll use a logarithm-based approach. The number of digits in a positive number n can be calculated using the formula floor of log base 10 of n plus 1. For example, the number 1000 has log base 10 of 3, and 3 plus 1 equals 4 digits. But directly computing the logarithm of our number would be challenging because it's very large. So we'll use properties of logarithms to simplify our work. Let's begin by working with 8 to the power of 17. We can write 8 as 2 cubed. So 8 to the power of 17 becomes 2 cubed to the power of 17. Using the power of a power property, we can multiply the exponents. So 2 cubed to the power of 17 equals 2 to the power of 3 times 17, which is 2 to the power of 51. Now, let's work on the second part of our expression, 5 to the power of 45. We can rewrite our original expression as 2 to the power of 51 times 5 to the power of 45. We'll now split 2 to the power of 51 as 2 to the power of 6 times 2 to the power of 45. This will help us combine terms later. For the next step, we can rearrange this expression as 2 to the power of 6 times the product of 2 to the power of 45 and 5 to the power of 45. The product of 2 to the power of 45 and 5 to the power of 45 can be written as 2 times 5 to the power of 45 using the product rule of exponents. Since 2 times 5 equals 10, we have 2 to the power of 6 times 10 to the power of 45. Now that we have our expression in terms of powers of 10, 2 to the power of 6 is equal to 64. So our number equals 64 times 10 to the power of 45. In decimal form, this is 64 followed by 45 zeros. Since 64 has 2 digits, and we have 45 additional zeros, the total number of digits is 2 plus 45, which equals 47. As a verification, we could also use logarithms directly. The number of digits equals the floor of log base 10 of our number, plus 1. Log base 10 of 8 to the power of 17 times 5 to the power of 45 equals 17 times log base 10 of 8 plus 45 times log base 10 of 5. Log base 10 of 8 is approximately 0.903, and log base 10 of 5 is approximately 0.699. So we have 17 times 0.903 plus 45 times 0.699. This equals approximately 46.9, and the floor of this plus 1 is 47. So we confirm that the number has 47 digits. In conclusion, we've found that the number 8 to the power of 17 times 5 to the power of 45 has exactly 47 digits. The key to solving this problem was breaking down the large numbers into powers of 10, which makes counting digits straightforward. Remember, for any positive number, the number of digits equals the floor of its base 10 logarithm plus 1. Today, we'll solve a problem about counting the number of digits in a large number. Let's look at our example. Let's start solving the problem. First, we'll rewrite 4 as 2 squared. This gives us 2 squared to the power of 16 multiplied by 5 to the power of 25. Now, we'll use the power of power rule, which states that when we have a power raised to another power, we multiply the exponents. So, 2 squared to the power of 16 becomes 2 to the power of 32. For the next step, we'll split the power of 2 into the sum of 7 and 25. So, 2 to the power of 32 becomes 2 to the power of 7 times 2 to the power of 25. Now, we'll rearrange the expression using the associative property of multiplication. We'll group 2 to the power of 25 with 5 to the power of 25. Inside the parentheses, we have 2 to the power of 25 times 5 to the power of 25. Since the exponents are the same, we can simplify this to 2 times 5, all raised to the power of 25, which is 10 to the power of 25. Now, we simplify 2 times 5 inside the parentheses. 2 times 5 equals 10, so we have 2 to the power of 7 times 10 to the power of 25. For our final step, we need to calculate exactly how many digits our number has. First, let's calculate 2 to the power of 7, which is 128. So our expression becomes 128 times 10 to the power of 25. Now, when we multiply 128 by 10 to the power of 25, we get a number that starts with 128 followed by 25 zeros. This is because multiplying by 10 to the power of 25 means adding 25 zeros to the right of 128. Therefore, our number 4 to the power of 16 times 5 to the power of 25 has a total of 28 digits. This is because it has the 3 digits of 128 plus the additional 25 zeros, giving us 3 plus 25, which equals 28 digits in total. Today, we'll solve an interesting expression involving exponents and fractions. Let's begin step by step. First, we'll rewrite our decimal numbers as fractions. 0.25 is equal to 25 over 100. And 10.24 is equal to 1024 over 100. Now, let's simplify further. We'll rewrite 25 over 100 as 1/4, which is 2 to the negative 2 power. We'll also rewrite 1024 over 100 as 2 to the 10th power times 10 to the negative 2 power. Now, let's use a power property. We can rewrite 1/4 as 2 to the negative 2 power. So 1/4 to the negative 3rd becomes 2 to the negative 2 to the negative 3rd power. Following the rule that when we have a power raised to another power, we multiply the exponents. So 2 to the negative 2 to the negative 3 becomes 2 to the positive 6. And now we need to distribute the exponent 3 to the terms inside the parentheses in the numerator. This gives us 2 to the 30 power times 10 to the negative 6 power. Let's work on the denominator now. We can write 25 as 5 squared. So 25 to the negative 18 power becomes 5 to the negative 36 power. Now, let's combine like terms. In the numerator, we can combine the powers of 2, getting 2 to the 36 power. For the denominator, remember that a negative exponent in the denominator becomes a positive exponent in the numerator. So our expression simplifies to 2 to the 36 power times 5 to the 36 power times 10 to the negative 6 power times 10 to the 8th power. Let's combine the powers of 10. 10 to the negative 6 power times 10 to the 8th power equals 10 squared, which is 100. We can also rewrite 2 to the 36 power times 5 to the 36 power as a single term. Notice that 2 times 5 equals 10, so we have 10 to the 36th power. In the final step, we combine 10 to the 36th power and 10 squared to get 10 to the 38th power. Therefore, the value of the given expression is 10 to the 38th power, which is a number with 39 digits, 1 followed by 38 zeros. To summarize, we solve this complex expression involving exponents by converting decimals to fractions, rewriting terms in standard forms, applying various exponent rules, and finally simplifying to get our answer of 10 to the 38th power. Welcome to this math tutorial, where we'll explore an interesting property of exponential expressions. This theorem states that for any positive real number a and any real number b, the following equality holds. Let's examine this theorem in detail. We start with our example. First, we note our assumptions. We assume that a is a positive real number and b is any real number. Now, let's begin our proof. We want to show that a raised to the power b equals the square of a raised to the power b over 2. Let's focus on the right side of our equation. When we have a power raised to another power, we can multiply the exponents. Let's apply this rule to the expression a raised to the power b over 2 squared. Let's apply this rule to our expression. When we square a raised to the power b over 2, we multiply the exponents. So, b over 2 times 2 equals b. Therefore, we have shown that the square of a raised to the power b over 2 equals a raised to the power b. This verifies our original theorem. It's important to note that the exponential expression a to the power b is always positive. This is because we defined a as a positive real number. No matter what value b takes, the result will always be positive. Let's examine why this expression is always positive. For the case when b is positive, it's clear that a to the power b is positive because a positive number raised to any power is positive. For the case when b is negative, we can rewrite a to the power b as 1 divided by a to the power negative b. Since a to the power negative b is positive, 1 divided by a positive number is still positive. Note that if b is negative, then negative b is positive. This completes our exploration of the theorem. To recap, we've proven that for any positive real number a and any real number b, a to the power b equals the square of a to the power b over 2. This property is useful in various mathematical contexts, especially when working with exponents and powers. Today we'll explore an important concept that often causes confusion in exponent rules. We'll explain the difference between a squared then square rooted versus a square rooted then squared. Let's start with our example. As we can see, in general the expressions a squared then square rooted and a square rooted then squared are different from each other. Let's analyze both expressions one by one. First, let's look at a squared then square rooted. We start with a squared, which gives us a times a. Then we apply the square root, which is the same as raising to the power of 1/2. Using the power rule for exponents, when we raise a power to another power, we multiply the exponents. So we have a raised to the power of 2 times 1/2, which gives us a to the power of 1. And a to the power of 1 is simply a. However, there's an important detail here. Since we're taking the square root, we need the absolute value of a. So the final result is the absolute value of a. Now, let's look at the second expression. A square rooted then squared. We start by taking the square root of, which gives us a to the power of 1/2. Then we square this result. Using the power rule again, we multiply the exponents. 1/2 times 2, which gives us a to the power of 1. So the result is simply a. But notice that in this case, since we first take the square root, we need a to be non-negative for the expression to be defined in the real number system. Now, let's compare the two results. For the first expression, a squared then square rooted, we get the absolute value of a. For the second expression, a square rooted then squared, we get a, but only when it is non-negative. When working with nested exponents, the order of operations matters. If we square first, then take the square root, we get the absolute value. If we take the square root first, then square, we get the original value, but only for non-negative numbers. More generally, this principle applies to all even roots. For any even integer, m, the expression root 2m of a to the power 2m equals the absolute value of a. Let's end with a challenge question. If it equals -3, what is the value of a squared then square rooted? Pause the video and try to solve it yourself. The answer is 3. Since there is -3, a squared is 9, and the square root of 9 is 3, which is the absolute value of -3. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.